Good evening and a warm welcome to Day 2 evening session of the 8th National Conference of Ocean Society of India, OSICON 23. Please join me in welcoming Dr. Mani Murali, General Secretary of the Ocean Society of India, to deliver the welcome address and introduce the speaker of the evening.
Good evening to all. So it's a pleasant evening. I'm privileged to welcome you all for this plenary session and OSI Fellows Award Function ceremony. It's my pleasure to introduce my senior colleague, my mentor, one of the gentlemen from NIO, Dr. Shenoy. When I joined the Physical Oceanography Division, he was one of the senior scientists over there, and I am indebted to him that who got me introduced into sea level rise studies at that time. So at this moment, I would like to, I think a lot of students are still available here to listen a great lecture today. So industry partners are sitting and scientists all over there. So on behalf of OSI, I would like to welcome all of you, each and every one of you, to this evening. Now, it's my duty to briefly introduce Dr. Shenoy, who started his scientific career from CSIR NAO, Goa. Subsequently, based on his scientific accomplishments, he earned a lot of scientific great credits and moved as a director in COIS, and he served here for a very long time as a director. And he also served as Vice Chair of the Intergovernmental Oceanographic Commission of UNESCO from 2019 to 21, Co-Chair of the IOEE Expedition 2 during 2015 and 22, and his credits are very, very long. So without wasting much time, it's my pleasure to welcome Dr. Shenoy to give his plenary talk on this great evening. Thank you, one and all.
Yeah, good evening, and thanks to Dr. Murali for generous introduction. And let me first thank OSI, especially the governing council of OSI and the local organizing committee director in COIS, Dr. Srinivas Kumar, for giving me an opportunity to deliver a plenary lecture. So the topic that I have selected is based on the work we were doing during the past 6 to 7 years actually. And this is a summary of the work which has been done over 2 PhDs by Rohit and Afruza, and Afruza's supervisor Arya Paul. And also we have collaborators, 2 French collaborators, Dr. Fabien and Romain, because we have used a French model to analyze the results. And also the last part we got stuck because we were getting into a field which we were not having complete expertise. I will tell about that. That is based on the Earth's rotation. So we were unable to clearly interpret the results there. So we roped in a scientist, Michael Schindler, from Germany. He's from Bonn University. He's an expert in geodesy. So that's how, but he came very recently because our last paper is based on that. So basically, I'm going to talk the work which has been done for 2 PhDs and the papers published in very respectable journals. I will give the list towards the end, or the 5 papers which has been published since 2019, and the last paper is under review in a journal right now. So that is the paper, and all the figures, I'm not going to give specific references, because any figure you will find either in Rohit's or Afroza's thesis or in those 5 papers. So I have taken from these 5 papers and the thesis, so I am not going to give a specific reference to any of that. So the topic is discovery of MJO-induced intra-seasonal barotropic sea level variability in the tropical Indian Ocean and the consequence. As you know that several tsunami buoys have been deployed, as that map shows all over the world oceans. And after the tsunami in Indian Ocean in 2004, India also started deploying these tsunami buoys. Right now, there are 7 buoys which has been indicated there, and that is providing the data. So when Rohit approached me and we wanted to plan his PhD topic, we thought that these buoys are giving data for the tsunami, but tsunami comes once in a while, may not come in our lifetime also. So, this is providing data on a day-to-day basis. Every hour that data is coming. So it should be used to see how the sea level in the open sea is varying, and try to find, analyze that, and see whether we will be able to explain why that sea level variability. That's how we started this work. So Rohit went and processed that data. It was a painful processing. It is not straightforward. So he did that. And then he came up with this plot to me and showed this plot and told that something is different during the winter months. December to April months, it is different. And it looks like we took 3 buoys actually, Bay of Bengal, another one in Arabian Sea, and another one in that Australian basin, that is that maritime continent area. So these 3 buoys data we started working with, and it was something unusual, like we thought that each one will show different kind of variability, but there is something very common, and it shows that something is different during these winter months than the other months. That is point number 1. And second is, it looks like all these buoys are showing, or the variability is almost the same time. So that was intriguing, because the Bay of Bengal buoy is something like more than 2,000 or 3,000 kilometers away from the Arabian Sea buoy, and the sea level variability which is happening in the Bay of Bengal, how it can happen at the same time at the Arabian Sea. So that was very intriguing, and we didn't have an answer for that for quite some time. Because I am going to use a word called barotropic, and I know that there are students from other disciplines as well, and they will wonder what is this barotropic. It is nothing to worry about. We physical oceanographers, we say that baroclinic and barotropic. Barotropic means every isotherm in the, if you draw isobars in the ocean at 0, 10 meters, 100 meters, 200 meters, like that, everything will oscillate at the same way. Or it is a mean picture of the ocean. That is what is barotropic. And if you look at the velocity picture, it will be same velocity from surface to the bottom. So that mode we call a zeroth mode or barotropic mode. And baroclinic means At the surface, the variability will be different from the middle of the ocean, and at the bottom, it will be different. So such motions we call baroclinic. So the beauty of this data is that because this data is collected by the tsunami buoy, that is a BPR or a bottom pressure sensor, which is sitting at the bottom of the ocean, and that is measuring. So that can measure both actually, baroclinic as well as barotropic. But if you look at the data, you will realize that that is purely barotropic, and baroclinic component in that is very less, or it is completely negligible. So what we are actually seeing is barotropic motion in that data. And if you look at that data, you will see other barotropic motions as well. One of them is, can anybody tell what is the other barotropic motion we will see in this data? Anyone? What are the other barotropic motions in the ocean? Any physical oceanography students? What about tide? Tide is a barotropic motion? Tide is a barotropic. So if you look at this data, the first signal you will see is the tides you will see. Okay? So the plot which I showed earlier, that was after the removal of the tide. So that's why it is written detided. So tide has been removed, and after that whatever is left out is what is shown there. Similarly, tsunami waves, they are also barotropic waves, because that's why this bottom pressure can get the tsunami waves. Otherwise, like surface waves, you will not get in this bottom pressure recorder, because they will die down after a certain depth. So you will not get that. So because the barotropic motion, that's why we are able to get that at the bottom of the ocean. So that's what it means, the barotropic motion means. So we took a spectra of this data, and we realized that these motions are very conspicuous within a certain band, or that is conspicuous between about 30 to 80 days band. That is what we call intra-seasonal band. So I am going to concentrate on those motions which has periodicities of about 30 to 80 days, 80 days periodicity. And the bottom figure, it shows the phase of these motions. As I told earlier, this, if you look at Arabian Sea versus Bay of Bengal, the first left one, which shows that the phase is same, because if the arrow is towards right, it indicates that it is in phase. That means exactly this variability within that 30 to 80 days period, it is happening simultaneously in Bay of Bengal and Arabian Sea. So that is the intriguing part of the entire study. That's why we were bewildered that how it is possible something happening in the Bay of Bengal simultaneously happening in the northern Arabian Sea, which is about 2,500 kilometers apart. Which wave can reach fast up to there, or what is causing this variability? And also similarly, Bay of Bengal and northwestern Australian basin buoy also, that also shows these motions are happening simultaneously, or they are in synchronous. So we filtered that with a 30 to 80 day filter, and the first panel shows that it is the 30 to 80 day band, or the intra-seasonal variability. And you can see that intra-seasonal variability is highlighted during the winter months. Other months it is a bit weak or not that much strong. So we will concentrate on that particular season, that is the winter season. and the 30 to 80 days variability. And this variability is happening not just at those locations, and it is happening all over the Indian Ocean. That means the entire Indian Ocean is going up and down with a periodicity of about 30 to 80 days period simultaneously everywhere. This is happening over the entire water column. That's why it is barotropic. And this is possible because we analyze the GRACE data. The GRACE data gives the how much mass in the ocean is there. So you take the GRACE data and then convert that mass into the equivalent water depth, similar to what the buoy has been reporting, and then filter that data to in that same time band, that is 30 to 80 days. And that is the picture which you will see that the entire Indian Ocean is going up and down with about 30 to 80 days periodicity. So that is what is happening. So the question is, what forced this basin-wide oscillation? What is the forcing? Who is doing this, or how it is happening? That's the first question. And what is the dynamics of this oscillation? How it is happening? So these are the two questions first intrigued us, and we try to find the answer for that. See, first thing which came to our mind, anybody will tell that, oh, this is because of the atmospheric pressure. That means if entire over the entire Indian Ocean region, if there is a high pressure, the sea level can be pushed down, or if it is a low pressure over the entire basin, it can come up. But there are studies which says that the atmospheric pressure will not do this, because it is only a hydrostatic adjustment what is happening. Because what we are measuring is the total mass of atmosphere plus the ocean water, so it cannot be atmospheric pressure. That is first thing. Other possibility is the winds are same all over. In the Bay of Bengal, Arabian Sea, everywhere is same. Simultaneously the winds are same. Then that can generate. But that also is not the reason. So what can force this kind of variability which is happening simultaneously in the Arabian Sea and the Bay of Bengal? So most likely is the coherent variability must have been generated by the fast moving barotropic waves. See, if a barotropic wave, if you consider, they will move fast. They can move fast from one location to other. And the baroclinic waves, they will take time. So for even to cross the equator itself, it will take months. It will take 2 to 3 months time. Whereas the barotropic waves are very fast waves, they can. But we don't know whether such waves are existing at that time. And we don't have an answer for that. But already there were publications that, yes, this is, if the wind is blowing over a larger area, more than 100 kilometers or larger area, then that can produce the motions in the ocean which can go up to bottom of the sea. So it is not only, of course, baroclinic motions it will produce, and the baroclinic, in addition to that, it can also produce these barotropic motions which can penetrate up to the bottom of the sea. And another possibility is that either the baroclinic energy is getting transferred to the barotropic mode. That also can make these barotropic oscillations. So we looked at the literature at that time. And if you look at the literature, there are studies, but all those are in the high latitudes. There is no study reported that there are barotropic sea level variabilities happening in the tropics. And as a physical oceanographer, I also never consider, or none of the physical oceanographers considers barotropic sea level variability is significant. So we all ignore that. We never bother about the barotropic sea level variability. So it was quite interesting to see that there is nothing in the tropics except in those enclosed seas. There are some 2 studies reported that. Otherwise, in the tropics, entire tropics is completely empty there. So we thought that then let us see whether where is that wind patch which is generating these barotropic waves which can travel fast from that location to all over the basin. So when we looked at the literature, the forcing function is coming from F over rho g. F is the Coriolis force, and the curl of the wind stress divided by h. It is not just wind stress divided by h. So it is tau upon h. So we did a correlation of the winds in that intra-seasonal periodicity with the Bay of Bengal sea level variability in that intra-seasonal variability. And as you see that, you can see that the correlation is happening only in a small patch of the area, not there. So that means the winds which are blowing there, those winds are forcing these waves, barotropic, something barotropic, and that may be the one which is propagating all over and creating those variabilities. So significant correlation in the eastern Indian Ocean or northwest Australian basin. And why that area is important? If you look at the MJO, that is Madden-Julian oscillation, it's an atmospheric phenomenon. It starts somewhere near the African coast, then it propagates towards northeast, and that brings our variability. Today morning, Dr. Rajivan also spoke about that, monsoon variability. When the MJO was active, we had plenty of rain about a few weeks back. Now the MJO has gone, and our rains also have gone from this region. So if you look at the MJO phase 3 to 6, that goes over that maritime continent region. That's the time it is happening, and it will be over the maritime continent region when the phase is 3 to 6. And if you look at those years which we analyze the data, the MJO is there over that maritime continent region or that small box region, and those winds are very strong during the MJO. So these winds, when they are strong in that area, is the one which can force these waves. So then we thought that if we had to understand the dynamics and explain how it is happening, we had to use a model. So we used that model, one model MOM for P1, and force that model with the winds all over the basin, and this is what we are seeing. So when we force the model with winds all over the basin, it is producing that kind of a variability. Actually, the gray is from the observation, and the other curve is from the wind forcing all over the basin. So we are able to get that that kind of a variability if we have the winds all over the basin. But then what we did is we shut down the winds everywhere. Only we kept the winds only over that maritime continent region or that square box region, and then again run the model. And you can see that that is explaining the variability. About more than 60% of the variability is forced by the winds there. So if you don't have winds there, you will not see these waves in the Arabian Sea or this kind of variability. So what is happening is that in the northwestern Australian basin is the prominent forcing region for this basin-wide barotropic variability. Now, if you remember that forcing term, that is tau over h, the curl of tau over h, that means h, how much that h can influence, that And also whether, as I told earlier, whether the baroclinic energy is getting transferred, do we need, if it is barotropic, you don't need a stratified ocean. Even if the ocean is barotropic or non-stratified, these waves we should see. But for that purpose, what we did is we made the uniform temperature and salinity of the entire ocean in the model, and then run the model again. And what we see is then it is producing the this variability, but it is 30% less. It is the magnitude is coming less. That means the stratification is required to get the waves at the same kind of a magnitude. What we have observed, that's what that experiment says. And to see how far that H is important, whether that H is required to produce these waves or not, we have flattened the bottom. The ocean bottom was made the same depth. There is no variability in the bottom topography, and then run the model again. And then that also says that it is less than 30%, and it is not able to produce the waves as it is what has been observed. So that means the stratification and the depth, these both are required to produce that variability in that intra-seasonal period. And actually this animation will show that when the winds are blowing in that panel where F del cross tau or H, that's the wind. When the winds are blowing, you can see that the waves are produced, and those waves are propagating all over the basin and filling the entire Indian Ocean basin. And the wind phase changes, it produces the negative, positive and negative. So the Indian Ocean is going up and down because the winds are blowing in that particular region. So to summarize, we have put everything in a schematic and calculated based on those speeds, what kind of waves they are, the theory, what it says, and from the models, what is the speed we are seeing. And we have summarized in this this schematic that these are that red arrow shows they are propagating as Rossby waves. They are fast moving barotropic Rossby waves. That's why they are fast moving, and topographic Rossby waves. So they are not going towards south. They are getting moving along that ridge region, and shelf waves. Barotropic shelf waves. So these waves can move at a very fast speed as indicated there, 50 meter per second. The Rossby waves are moving, and shelf waves are moving at 6.5 meter per second, whereas baroclinic waves moves at centimeter speed, and these are moving at a meter per second speed. So the conclusion is that that is the barotropic sea level variability at intra-seasonal periods are caused by, one is the MJO winds in the northwestern Australian basin, and second is that varying topography is important. Without that, you will not be able to produce the waves as seen there. And the third is the stratified ocean is required. So these three conditions, if it meets, then it will produce this kind of waves which will invade the entire basin quickly, and then you will see that these oscillations are taking place simultaneously all over the Indian Ocean basin. But the issue is these oscillations which are happening, whether they are happening only over the Indian Ocean, and that cannot be, because if the sea level is going down, then from somewhere the water should come there. Otherwise, when the sea level goes up, the water should get pushed elsewhere. And the westing can happen is on the eastern side, because through the Indian Ocean through flow region and below the Australia. So we just picked another BPR from the Pacific, and then did the same kind of processing on that also. And that plot shows that, yes, when Indian Ocean sea level goes down, you can see that they are in the opposite phase. That black curve and magenta curve, they are in opposite phase. That means when the Indian Ocean the sea level goes up, the Pacific sea level goes down, and vice versa. When the Pacific sea level goes up, Indian Ocean sea level going down. And the model also, if we expand there, I don't remember this model or from the Grace data. That's Grace data model. Yeah, model also shows that you can clearly see that they are in the opposing phase, and this kind of oscillations are happening in both of the oceans. So that means what is happening is, so we got interested in that, and we thought that we should also look at little more detail over the Pacific, and picked more BPRs from the Pacific. And all this data is available on the NOAA NDBP website. Anybody can download and use that data. And we picked more BPRs and did a correlation between this. And you can see that it is opposite. All Indian Ocean BPRs having one color, and other one is the opposite color. And that means it is playing a seesaw at that 30 to 80 days period. The Indian Ocean sea level goes down, and the Pacific sea level comes up, and vice versa it is happening. So this is a very intriguing, and nobody has reported before this kind of a seesaw which is happening. And this is happening in the barotropic realm actually. So this suggests that there is a seesaw between Indo-Pacific oceanic mass. So the water is moved, getting sloshed between Pacific and Indian Ocean at this periodicity is about 30 to 80 days. The water is getting sloshed between this. And this seesaw is very intriguing. So we thought that we should do a little more analysis of this. Otherwise, nobody will buy this idea because nobody has told so far. So we used them, and somebody should not tell only your model will show, no one else will show that. So we thought that we should use a suite of models, and we picked whatever models we could put our hands. So we picked about 5-6 models. Of course, they are all having different resolutions. Some are at 1 degree, some are at half a degree, some are at quarter degree, some are at 1/12th degree. And every model, when we did analyze that, every model is showing this kind of a behavior. That is at that intra-seasonal frequency, the barotropic sea level is in a different opposing phase in the Pacific as well as in the Indian Ocean. Of course, some of the models are not doing exactly the same, but by and large, that general picture is the same from every model, because the model resolutions are different, and except HICOM and NEMO model, other models are higher resolution, the resolution is poorer, and these are 1/12th resolution. And except HICOM, the HICOM is outlier. It, in spite of that 1/12th degree resolution, it could not give exactly same like the NEMO model produced. Otherwise, it is, that also is showing that it is reproducing those results. The reason for some of the models to give the lesser accuracy is that they may not be able to resolve that Pacific through flow region. For example, if you look at those major straits in the Indonesian through flow region, Ombai is only 30 kilometers wide. So if you use a 1 degree model, that no water will come through that. Lombok is 35, and Timor is just 80 kilometers. So you need a finer model to resolve those narrow straits in the Indonesian region. So to analyze this further, we defined two numbers, because rather than keeping it wider, if you can distill this in some sort of an index or some number, then it is much easier. So we defined a index called seesaw index, that is variability of barotropic sea level in the Indian Ocean minus barotropic sea level in the Pacific Ocean, and to compare the same across the models, because models have different variabilities, different standard deviation, etc. So we normalized that. So we used further this index, what we call seesaw index, and the normalized seesaw index for further comparisons. So the issue is that then how much water can pass through this Indonesian region, because if you look at the Indonesian region, they are very narrow, narrow straits, point number one, and they are not very deep like the other sides. So whether the Indonesian region is playing a major role or nothing, it is passing through. If you ask many of the physical oceanographers, they will tell that it is not much. You can compare to the other passage, it will not pass much water through that. So to see how it is behaving, we closed that. In the model, we closed the Indonesian region. All those straits are closed and run the model. And then it clearly shows that if you close, you will not get this. You will not see that, you can see that in the Pacific, though the Indian Ocean, because it is forced in the Indian Ocean, it is producing the Indian Ocean variability, but it is not able to produce the variability over the Pacific region. So that means the Indonesian through flow region is very important in producing this seesaw, because it has to exchange the water through Indian Ocean region, that through flow region. So thus the barotropic transport through the Indonesian straits is playing a major role in producing intra-seasonal Indo-Pacific seesaw. Otherwise that seesaw cannot be that effective. And other experiment what we did was, now both basins are in the model, both Indian Ocean as well as Pacific. So we put the winds only in that box area, like the experiment we did earlier. In this this model also, we blocked the winds, the other locations, and it is producing then. So that means in that small area, that those winds which are blowing, actually if you look at that box, it is not more than 4% of the total oceanic area, global area. But it is influencing about 90%, more than 80% of the global ocean area. So this small region, that is enough to produce this variability, not only over the Indian Ocean region, but also over the Pacific also. So the winds there, you just churn there, it is producing this kind of variability over the entire tropical Pacific and the Indian Ocean region. So we calculated what is the relative variance in this variability in the Indian Ocean and Pacific Ocean. So it turns out to be that relative variance, about 60 to 70% of the variability in barotropic sea level in the Indian Ocean, and about 15 to 30% of the variability in the Pacific Ocean is caused by the MJO winds in that maritime continent region. That means that small region, the winds are able to produce much wider variabilities over the Pacific as well as over the Indian Ocean region. So what is the wave dynamics now? In the Indian Ocean, we saw that those fast moving Rossby waves, and then the shelf waves and the topographic Rossby waves they are fast moving and they are moving fast and they are creating that variability. It's the same thing is happening over the Pacific also. So we did the same analysis over the Pacific also. And it turns out that the equatorial Kelvin, barotropic equatorial Kelvin waves, they are moving at 150 meter per second. They are quite fast. And the Rossby waves, then the coastal Kelvin waves, these are all barotropic waves. And the shelf waves, the same what we saw earlier. So they are all moving at these kind of speeds and creating this variability over the Pacific also. So the fulcrum is at the maritime continent area or that Indonesian through flow region. The winds blowing there, they are creating this variability over the Indian Ocean as well as over the Pacific Ocean. And within 5 to 6 days, the entire place gets affected. So that's why, of course, when we say simultaneous, it is not exactly pinpointed. It takes about 5 to 6 days time for these waves to travel, and it is very fast compared to the oceanic phenomenon, compared to any other phenomenon. So, so when this is happening, how much water is getting transported? That's the next question. Because we say that this seesaw is happening, water is getting exchanged, but we had to quantify how much water is getting transported. So we estimated that transport through the Indonesian region, Indonesian through flow region, as well as it can come all across the Australian, south of Australia and enter the Indian Ocean. And when the water comes from the Pacific, from the south it can move towards Pacific also, that green line, across the green line. So when we computed that, you can see that about 7 to 8 subgroup of water is getting involved in this. One subgroup is 10 to power 6 cubic meter per second. That is one subgroup. So that much water is getting transported through this seesaw across the basins. And yeah, this is just a schematic. And on an average, about 2.6 subgroup of water is entering from the Pacific through the Indonesian through flow, as well as from the Australian, south of Australia into the Indian Ocean. And then it is going back to the Pacific at these intra-seasonal frequencies. So if you analyze further, you can see that actually the water is entering through the Indonesian through flow region or that maritime continent, and going out, making a round to the Australian continent. And in the Pacific, it is in the opposite direction. And during the negative phase, it will reverse, and it will get into the Pacific, and the water will go out from the Indian Ocean region. So it is there is a seesaw which is exchanging about 2.6 subgroup of water at this 30 to 80 days periodicity between these two basins. And if you see that the pathway is, it is entering from that Malacca Sea region where that arrow shows. It comes to that Lifamatola passage, then Ombai Strait it goes, and then to the Indian Ocean it goes. Then another branch from there that also goes through the, that also enters from the Malacca Sea, then to the Flores Sea, and then Lombok Strait, and then goes to the Indian Ocean. So that is the pathway through which this water from the Pacific is entering the Indian Ocean, and then it goes around the Australian continent, goes out to the Pacific, again it comes in, and similarly during the negative phase, it is going out of the Indian Ocean also. So if that kind of a mass is exchanged, physics says that if you change the mass of the rotating body, its rotation speed will get affected, first thing. And if if that mass is not uniformly distributed, then it will wobble. It will not like that this doing there, it will start wobbling, because if the mass is not distributed uniformly, that's what the symbol physics says. But there are studies which says that so these are the two possibilities, because we are exchanging about 2.6 drop of water from Pacific to Indian Ocean and then taking it back. So that means the mass increases in the Indian Ocean, then it goes back to the Pacific, the mass will increase there. And in doing this, the mass is getting exchanged either way. So we looked at that possibility. So does it affect the Earth's rotation then? What it does to the Earth rotation because of this mass exchange is happening. But when we looked at the previous studies, it says that the ocean, because the rotation is happening because of the geodynamic contribution, then the atmosphere is there, then the ocean is there, then the hydrological adjustments are there. So the sum total is determining the Earth's rotation as well as the wobbling of the Earth's axis. So where this ocean change is contributing, the previous study says that ocean is not contributing to the rotational periods, or it cannot change the Earth's rotation by milliseconds. But the possibility has been told is that the entire world ocean, it contributes to about 30% of intra-seasonal variability of polar motions. So in the polar motion, if you plot that, you will see that same variability or same periodicity is there. With that periodicity, 30 to 80 days, this axis is wobbling there. So that people have shown that about 30% of the contribution is coming from the ocean, because ocean, the mass exchange happens everywhere. But the question is what our fellow is doing, how much it is contributing to the to this mass exchange. And this is just to explain that the wobbling is represented on the two axes. One is along the 90 east meridian, and other one is along the Greenwich meridian. So these are the two axes normally the geodetic people consider to look at the Earth's wobbling. And by the geometry of our configuration, because we are close to the 90-degree east meridian, so we should look more along that axis, how much wobbling that axis it can contribute. So that is the y-axis in the geology people, they call that as a y-axis. And we looked at that using again the model data, as well as there is an organization called International Earth Rotation Observation Services or something like that, where they monitor the Earth's rotation and keep this data. So if you look at that data, that is that grayscale gray this showing, and then we have looked at the oceanic excitation series examined from the control experiment. That means the winds everywhere, and by switching off the winds in other locations other than that maritime continental region, that is the blue curve, you can see that the blue curve is also not insignificant, it is contributing there. So that means those winds which are producing this variability and this mass exchange between Indian Ocean and Pacific Ocean, that also is contributing significantly to the wobble of the Earth. But how much it is? That is the question. So that also has been looked at, and this is the global contribution to that y-axis wobble, and the blue is the contribution coming from the Pacific, and green is coming from the Indian Ocean, southern Indian Ocean region. So if you quantify that, about 30 milli-arc second, because the wobble is accounted in the unit of milli-arc seconds. So out of about 30 mass of ocean, of which 20 milli-arc second is originating from the barotropic dynamics powered by the MJO winds. So that means out of 30 contribution coming from the ocean, about 20 milli-arc second is coming from because of this Gotala which is going on in the maritime continent region, which is forcing the mass exchange at the rate of 2.6 milli-arc second across the between Indian Ocean and Pacific Ocean. So and the red is showing the Indo-Pacific, that is the total, and that Indo-Pacific is contributing, that is what we are interested, and that is contributing to 20 milli-arc second. So let me summarize and conclude my talk. So we started with here, that time everybody told that barotropic sea level variability can be insignificant, you can neglect, you need not worry about that. And nobody used to consider that variability. And there are no studies in the tropics at all. And the first paper filled that area. We told that no, you cannot neglect that. When the variability in the total sea level, if you look at the Aviso sea level, it is about 8 centimeters, and this is contributing about 4 centimeters. So you cannot neglect that. So we filled the Indian Ocean with that color. And later we said that not only the Indian Ocean, it is over the Pacific also. So we filled that map with 2 large areas, and we state that you cannot neglect barotropic sea level variabilities in the tropics as well. And this has repercussions not only on the Earth's wobble. When you look at the mass contribution, mass budget between the oceans, you cannot neglect this. You have to consider this. Also, in correcting the altimeter data, you cannot just use take shelter under neglecting these kind of variabilities. So these are the conclusions which came out from. I don't want to read one by one. So the first is we established that there is a barotropic sea level variability in the tropics, and second is this at the intra-seasonal period, and it is happening mainly during the winter months, and the dynamics is coming from the fast moving Rossby and Kelvin and other type of waves, and associated with this intra-seasonal variability in the tropical Indian Ocean, similar out of phase variability is seen in the Pacific. So that leads to the seesaw like movement between these 2 basins, and the fast moving barotropic waves allow the entire Indo-Pacific basin to climatically adjust to MJO. Earlier theory says that for the ocean to adjust to the MJO response, it will take months, 3 to 4 months, but this shows that it can be simultaneous, or it can be at intra-seasonal scales much quicker. So the question which comes, I think Arya is waiting for a good student to look at further effects on SAM or other effects, as well as yesterday I was discussing with Arya, I was suggesting we should also look at what is the contributions on the conveyor belt, because it's a barotropic, how much heat, because the Indian Ocean is warming, heat is getting transported from Pacific, etc., etc. So whether this is helping in faster transport of heat from one basin to other, I don't know. If a good student comes, we can look at these issues. And this is the list of publications, the 5 papers which I mentioned, up to 4 it has been published in good respected journals. First one is in Nature Communication, and then Ocean Dynamics. Then again another nature group journal, Communications, Earth and Environment. Then Deep Sea Research Part 1, and other one is sent to Pure and Applied Geophysics. It is under review with that journal now, which talks about this Earth's wobbling. That's where we had to rope in an expert in geodesy also in the for this work. And these 2 theses submitted by Rohit and Afroza. So actually I spoke on behalf of all of them, and they did the hard work, I must say that. And I just summarize the work which has been mainly done by Rohit, Afroza, and the theoretical backup or advices given by Arya Paul. So, and of course our collaborators from France, Fabian Durand and other person. So with this, let me conclude this lecture. Thank you very much.
Okay. Do you want to take questions, sir? Yeah. Any questions?
Sir, thank you very much for an exciting talk. Sir, I have 2 questions. Yeah. One is that what I feel is that there is no net transport associated with this seesaw. It's like an AC current. Whatever comes in gets back. So the situation is like 2 balloons connected by their neck, and both are filled with water. One be pressure, the other bulge, and if you release, the bulging comes back. So you are interpreting the through flow water enters and going to make a full rotation. As such, the water will not come, but it immediately switches the water to the left, and in the next 90 days goes to the right. So as such, the water stays wherever it is, looks like. So because you are trying to see how much it will contribute to the conveyor belt and heat transport. So to my understanding, this will not create any net transport.
Yeah,
What stays, it stays there.
Yeah.
Second question is that, sir, 4 centimeter bulging, enter Indian Ocean. If you integrate the volume, in 90 days, will that suffice for sweater of transport that you expect to enter from the Pacific? Will that mass be balanced? This is my second question. Thank you for a wonderful talk, so much enjoyed.
Thank you. Yeah, the answer to your first question is I agree that there won't be any net transport of mass. But when the warm water comes, it can leave the heat, right? Heat, it will not take it back. So it can contribute to the heat, but without contributing the mass there. I bring some hot rod and put on your hand and take it back. The mass is gone back, but you get the heat, right?
But it's not conductive heat, it is a transported heat. If it's a conductive heat by contact, it can stay back, but it's a transported heat because heat transport is integral of velocity into temperature. So velocity goes back, temperature has to goes back with
Yeah.
I mean, that's my first interpretation.
I know that it's a little difficult to get that, but I believe that it must be conducting the heat. Yeah, actually I forgot to mention that when the seesaw happens, the Indian Ocean sea level goes up by about 4 centimeters, right? 4 centimeters.
But this through narrow strait, this much water is getting transported to the other area. So that means there should be a flooding in that short strait.
Yeah, sea level will go up at that time. Then it will go down. And in the Pacific, because Pacific a larger area,
Yeah.
So the Pacific sea level reflection is about 1.5 to 2 centimeters.
So in the related thing actually, the same question. So thing is that is it possible that instead of having one Rossby wave here and then one Kelvin wave the other side, is it possible to have a Rossby wave excited which has a wavelength of the Pacific and Indian Ocean? So you always get a phase in one phase in the Pacific and the other phase in the Indian Ocean.
Yeah,
Is it possible? Because there is a barotropic and the wavelength probably very large.
my first question to you is how you will excite that kind of a Rossby wave which will travel from one end to other. Second is that whatever that's shown there is based on the model results which using a technique called, what is that technique which you used to head-on technique. Using that, those speeds have been derived and compared with the theoretical speeds of these waves.
So how does it actually justify when you actually close the this one ITF and then the Indian Ocean sea level goes up, but from where it get compensated actually in that case?
No, see what it shows is that only Indian Ocean part when it is closed. So the waves can travel in the Indian Ocean itself. It is.
Okay, no, you suggested there is a seesaw, so it has to compensate from the Pacific.
Yeah, exactly. But when we close, that it's not reflecting in the Pacific region.
Yeah. Okay.
Yeah.
Nice talk. There are only small comments actually. One thing is how much percentage of this two sword group constitutes to the total ITF if you take baroclinic transport also? How much?
I think I don't remember. Do you have an answer? My
11 to, okay. So 20% you can say. 20%. Okay. No, total ITF.
question is
Yeah. So the total is
ITF.
about 11 to 21 swag groups, depending on which study you refer. So there is a range.
Second thing is that now this much is covered. So if you are to look at Atlantic, you may get
Atlantic. Actually, I didn't bring that Atlantic. We did look at the Atlantic buoys also, and very weak signals are seen in Atlantic. So we kept Atlantic aside.
So that is not giving any extra information.
No, not giving any extra information.
Okay.
I don't know whether we are missing anything there.
Thanks.
Because of this MJO. The MJO reaches that region during the winter months. Intensity, yes. That's why that final calculation is based on 2012-13, that period, when the MJO was very strong. Yeah, MJO intensity affects this.
Yeah, I think this can be a never ending. So, but we should put a full stop.
Thank you.
So, I sincerely thank Dr. Shennai for a wonderful work, global work, and we are very, very proud of you, sir. So, we sincerely thank you for accepting this offer and delivering this plenary session talk. Thank you very much, sir.
Thank you.
Huh?
I would like to make a small announcement. There's a change in the schedule. We will have the industry talks after the award ceremony. Sorry for the inconvenience. It's now time to celebrate excellence. Dr. M. Baba, former director CES, will give a glimpse into the prestigious OSI fellowships and awards that recognize outstanding contribution in the field. Welcome, sir.
Thank you. I will directly go into my responsibility. The Ocean Society of India in the recent times have taken a decision to give fellowships to outstanding professionals in the area of science and technology. We have two types of fellowships. One is a fellowship for the members of the society, and the second one is a honorary fellowship for those who are outstanding from the society and outstanding in the field. So I will just briefly tell how these fellowships are how defined and how the fellows are selected. Life members of OSI who have made outstanding contribution to ocean and allied fields of science and technology are selected as fellows by the general body of OSI on a proposal from the governing council. We have a governing body and a governing council. The total number of fellows shall not exceed 2% of the total number of life members registered on or before 31st December of the previous year. That is the condition. In 1 year, not more than 2 fellows are selected. Fellows of OSI, a fellowship of OSI is confirmed to the most outstanding or distinguished Indian researchers and other professionals in the areas related to oceans, working anywhere in India or abroad, in recognition of their contribution to the field of oceanography and related fields of exceptional merit. A minimum residency period of 10 years as a life member of OSC is mandatory for the fellowship. Whereas for honorary fellows, non-members of OSI also are selected. There shall be, again, there should be highly distinguished personnel in the areas related to oceans. Persons of acknowledged eminence in ocean sciences and allied fields, or they are further selected as honorary fellows by the general body of the OSI on a proposal from the GC, General Council. The total number of honorary fellows in OSI shall not exceed 1% of the total number of life members registered on or before 31st of December of the previous year. In 1 year, not more than 1 honorary fellow is selected. Honorary fellowship award is through nominations by GB on recommendation by the GC. Now I will tell you what is the criteria for the fellows. Personal achievements in scientific research, education, innovative development in technologies, as evident from the original scientific publications of high standards, patents for new products or processes, innovative processes that have significantly contributed to the development of the country and in particular in ocean development. Eminence in developing new and innovative fields in ocean science and technology. Eminence in developing ocean scientific institutions or departments and managing them, including membership of international ocean-related bodies, either of these. Outstanding contributions in the growth of Ocean Society of India, such as services rendered as a member of GC, organizing committees of OSI events, its publications, is given an additional advantage. Then selection of fellows are from among nominated persons, and a list of specified persons may be authorized to make the nominations. Each nomination should be seconded by another authorized person. The suggested list is honorary fellows or fellows of OSI, members of the prevailing GC of OSI, vice chancellors or heads of other institutions in the field of ocean science and technology. The nominations for the above fellowship should be submitted only in the enclosed performa. There is a performa for that by the person who is nominating. That should be submitted before 31st of 31st December of the previous year. All nominations received for consideration of fellows will be evaluated by a duly constituted fellowship selection committee by the GC. A candidate once nominated would be considered 3 times in a row. A record of nominated fellows each year to be maintained, and the list of eligible candidates from the previous years to be put up to the selection committee by the General Secretary. The GC will give its recommendation to the GB for its approval. The selected fellow or honorary fellow shall be conferred the title during the OSICONs or other major events of OSC. The fellowships are to be abbreviated as FOSI, that is for fellows, or FOSI bracket honorary, as the case may be. So this is the fellowship program of OSI, and I leave the rest of the things to the concerned persons. Thank you.
Thank you, sir. I invite Professor Prasad Bhaskaran, Vice President of OSI, who will now announce and read the citation of OSI Honorary Fellow for the year 2022.
So, good evening. The Ocean Society of India has been conferring the honorary fellowships to highly distinguished professionals of eminence in ocean sciences and allied fields. This year, in 2023, the honorary fellow is conferred to Professor P.B. Joseph. So, Professor Poratur Warid Joseph, born in Kerala on 29th of December 1932, got master's degree in physics from the University of Madras in 1953. The following 4 years, he taught physics at the University of Kerala, SB College. In 1957, he joined the India Meteorological Department, IMD. The first 5 years, he did work in geomagnetism at Kolaba and Alibag observatories, Bombay. During 1962 to 1963, he was trained in meteorology and weather prediction. And following 16 years, he did operational weather forecasting, cyclone warning, and aviation meteorology. Dr. Joseph was the director of the Meteorological Training School of IMD and WMO at Pune during 1980-1989. In 1983, he was awarded PhD in physics by Pune University for the research on monsoon variability. Taking voluntary retirement from IMD in 1989, Professor Joseph took up various research assignments in India and USA. He was emeritus professor at CUSAT during 1997 to 2019. So Professor Joseph has done original research for more than 5 decades in tropical meteorology, which includes monsoon, cyclones, and thunderstorms, and ocean-atmosphere interaction. He discovered a low-level jet stream in the monsoon circulation, the role of oceans in monsoon onset dates over Kerala, and in intra-seasonal oscillations in the monsoon is another area of his research. So Professor Joseph showed that an instability in the ocean atmosphere system causes frequent monsoon droughts in epochs lasting a few decades, like in 1961 to 1990. And for the research in atmospheric physics and hydrology, he received the Dr. Vikram Sarabhai Award in 1978. In 2012, he was the recipient of the Swadeshi Science Puraskaram, and in 2016, the Ministry of Earth Sciences presented him the National Award for Excellence in Atmospheric Science and Technology. In recognition of his outstanding contribution to education and research, the Indian Meteorological Society, IMS, presented him the Lifetime Achievement Award in the same year. Professor Joseph was honored by IMS by presenting him the Gilbert Walker Gold Medal in 2022 for his outstanding contributions to monsoon meteorology. Professor Joseph was an active member of the meteorological working groups and field experiments, both national and international. He is a fellow of the India Meteorological Society, member and 2 terms the president of the Ocean Society of India, and emeritus member of the American Meteorological Society. So considering his outstanding contributions in the field of ocean and related sciences, the governing body of the Ocean Society of India is pleased to confer the OSI Honorary Fellowship on Professor Poratur Warid Joseph on this day, that is 23rd of August 2023, on the occasion of OCCON 23. And due to poor health condition, Professor Joseph is unable to physically attend OCCON 2023 at Inquise, Hyderabad. Hence, the Fellowship Award has presented to him at his residence in Cochin on 13th of August 2023. And a video of this presentation and Professor Joseph's message will be displayed now. Thank you.
So this is the citation. Good morning to all of you. I am very happy to participate in this meeting. In 2006, we all, large number of scientists of Cochin assembled in MPOL and then laid the foundations of the Ocean Society of India. And from that year onwards, it was growing in numbers, membership. Well, now we have reached almost 600 members. And there is a parallel society, Meteorological Society, Indian Meteorological Society. These two, my wish is that they collaborate and we cover the two media, atmosphere and the ocean. My earnest wish and prayer is that Ocean Society of India may grow in membership and do all the kind of actions that are needed to develop meteorology and oceanography and disaster warning systems. I take this opportunity to thank all the departments in India which supported the growth of Ocean Society membership, and wish success for the OCCON 23 conference held at Hyderabad.
We move forward to celebrate excellence yet again. Shri Patabi Ramarao, convener OCCON 23, Group Director INCOIS, Vice President OSI, will now announce the OSI Fellow for the year 2023.
Good evening, everyone. The Ocean Society of India has a fellowship program for its life member who have made an outstanding contribution to the ocean and allied fields of ocean science and technology. I have the honor and privilege to announce that the OSI governing body decided to confer the fellowship of OSI on Dr. Sadananda Satish Chandra Shannai for the year 2022. Dr. Sadanand Satish Chandra Shannai did his MSc and PhD from CUSAT, Kochi, and PDF at Rosenstiel School of Marine, Atmospheric, and Earth Science, University of Miami. Dr. Shannai contributed significantly to the understanding of currents around India, which facilitated the development of a theoretical framework to explain them. His research on the role of the Indian Ocean in monsoons changed the traditional view of ocean being a passive player in the monsoonal process. He showed that the regional optimization of algorithm coefficients could improve the estimation of sea surface temperature using IR sensors by 50% over the Indian Ocean. He initiated the long-term direct measurement of currents in the Northern Indian Ocean using current meters, satellite tracked drifters, and moved ADCPs. He coordinated the research that improved the estimate of the extent of 2004 Indian Ocean tsunami source region. Dr. Shannai led the establishment of Ocean State Forecasting Services and the International Training Center for Operational Oceanography, a UNESCO Category 2 center at INCOIS. His recent collaborative research includes the discovery of intra-seasonal barotropic oscillations in sea level in the tropical Indian Ocean excited by MJO winds in the maritime continent, causing a seesaw of ocean mass between the Indian and Pacific Oceans, impacting the Earth's polar motion. Dr. Shannai served as Director, Indian National Center for Ocean Information Services, Hyderabad, 2009 to 2020, and also as Director, National Institute of Ocean Technology, Chennai, during August 2015 to February 2018, and Project Director, Integrated Coastal and Marine Area Management, Chennai, during August 2015 to July 2016. Dr. Shannai is a Fellow of Indian Academy of Sciences, National Academy of Sciences, India, Indian Geophysical Union, Andhra Pradesh Academy of Sciences, and Telangana State Academy of Sciences. He is a recipient of Dr. H.N. Siddiqui Memorial Lecture Award 2011 from IGU, Doctor of Science, honoris causa in 2016 from Amet University, Chennai, and the National Award for Ocean Science and Technology from Ministry of Earth Sciences 2018. He served as Chair, Co-Chair, Vice Chair, member of international commissions, steering groups, associations, etc. Since 2022, he has been serving as the National Vice President of Vijnana Bharati, VIBA. Considering his outstanding contributions in the field of ocean sciences, the governing body of the Ocean Society of India is pleased to confer fellowship on Dr. Sadanand Satish Chandra Shannai on this day, that is 24th August 2023, on the occasion of OCCON 23. Thank you.
I invite Dr. S.S.U. Shenoy to the dais. I request our Director, Dr. Srinivas Kumar, and Dr. N.P. Kurian to join. I request our Director to adorn Shenoy sir with a shawl and present the citation. I request Dr. N.P. Kurian to present the memento. Yeah. We also have a small memento from Incois. Big memento. Thank you, sir. Thank you. We will now have the industry talks. We have a series of enlightening talks from our esteemed representatives. I invite Mr. Asar Awad, Technical Sales and Training Manager, Impact Subsea, collaborator of Pan India. Call a mic. Yes, sir. Before we begin, I request Dr. Shenoy to say a few words.
Thank you. I don't want to say anything more because already a long lecture you have tolerated. I just want to say thank you to Ocean Society of India for selecting me for this fellowship. And also I must thank all my collaborators at INCOIS as well as at NIO earlier, who collaborated with me for various research activities. And all my colleagues, because my last leg was of the professional life was at INCOIS for about more than 11 years. So I must thank each and everyone at INCOIS for all encouragement and support, and also for scientific discussions. Thanks to all of you, especially to Ocean Society of India. Thank you very much.
Hello everyone. I hope you hear me fine because I cannot hear myself well, to be honest, but yeah. My name is Asar Awad. I work for Impact Subsea. It's a subsea sensors manufacturer based in the UK, but we are represented here in India by Pan India. So I'll start with a bit of introduction about Pan India so that you can know what they're doing here. So Pan India started operations in 1981, so they have over 40 years of experience now in the industry. They are ISO certified and they are a member of the Society of Defense Manufacturers. So to give you a bit of what they're doing or the domains that they're working in, they are in geophysical and geotechnical solutions, defense technologies, search and rescue. They also do system integrations and different other things. Also, they participate in Make of India, so they've developed different kind of systems, such as the DAPS, and also they developed the Parth 1000 IMU motion sensors, and they are the winner of IDEX Disc 7 Sprint Challenge for the Indian Navy. Yeah, so coming to Impact Subsea. So as I mentioned, we are based in the UK, in Scotland. We are a subsea sensors manufacturer. So I'll be going through 3 major sensors. I'll give you a bit of introduction or a bit of the technology background of the technology that we're using in our sensors so that you can know how is it working, and you will decide for your projects or your research which kind of sensors you can use. So starting with our ICE A500, it's an altimeter. with a 500 kilohertz as a center frequency, and it's a 6 degrees conical beam width. Regarding the technology, we are using a single board, no screws inside the sensor, so it's very immune to different kind of shock and vibration. Also, we are using a composite transducer, so the transducer itself, it's sliced and diced inside it, so it's very sensitive to the sound wave, so you can hear even lower than the ambient noise when you use it. Also, we use a digital correlation technique, so, and this is something probably one of the newest technology that we're using. We have an algorithm that runs around 2 million times a second, and that's also give it like really a great jump in the technology and the capabilities that we're going to talk about in a minute. In terms of capabilities, we have an over 120 meter in range. The photo is horrible, sorry about that, but here the altimeter is pointing at another side, the other side of that pool to basically measure the distance or the length of the pool, and it gives here 140 meters, so that gives you kind of example of our range. The other thing is totally something that set kind of new standard in the market. We have a 1 millimeter accuracy, which compared to the old altimeters, all the other altimeters in the market, we're talking about centimeters. So whenever you think about something that you want to measure as a distance underwater, the altimeter is a kind of good choice for that. It's most of the settings are user selectable, so you can use it in different ways. One of the most important thing is the frequency. Because we're using a composite transducer, we have a 400 to 600 kilohertz range of frequencies. You can choose or you can tune it the way that you want. So if you want to use different kind of altimeters at the same application close to each other, or you have other equipment that works at the same frequency, that can be a good option to tune them away from each other. Also, we have 3 different detection modes, so it will work in different kind of environments subsea. I'm not going through a lot here, not to take a lot of your time, but the most popular one is what we call it the strongest echo, and the way it works, it's that it sends the sound wave and listens to all the returns and compare them and give you the strongest one. And this is very useful if you have kind of a murky water, and if you use any of the altimeters, it's usually you get some unstable readings. It will be jumping all over the place. So with the strongest echo, it will still give you the highest or the strongest return, which will be the seabed. Okay, I'll try to wrap it up. I'll give me 2 minutes. Okay. So the second thing is the ISD 4000. The ISD 4000, I'll try to go through it quickly. We're using temperature compensated piezoresistive transducer when compared to the quartz system, which is one of the most popular systems in the market. You have a better shock and vibration and a non-blockable port and different other things that's really compared to with the temperature compensated piezoresistive, it's much more robust. We use a castellated cover, and we have an external RTD, so it have like a low latency and a high accuracy when it measures the temperature. So the ISD 4000 is actually a pressure gauge or a pressure sensor, and it has an accuracy of 0.01% over the full scale, and we can offer now a 0.005% over the full scale, which now got the accuracy of the quartz systems, and that made it very useful in different kind of applications. And the most popular one that started using this now is the tsunami detection systems because of the high accuracy, and at the same time, you get all the benefits from using the piezoelectric or the piezoresistive transducers. And 0.01 degree for the temperature accuracy. And a very high data rate. I'll skip the last one just to give opportunity for the other speakers as well. And yeah, thank you so much for that. Yeah.
Thank you, sir. I invite Mr. Sai Venkateshwar Reddy, Manager Pre-Sales from ESRI India, to deliver.
So nothing to be said. Yeah, good evening. So I'm going to, in this session, I'm going to talk on ISRI technology solutions and trendings. So in the interest of time, I will be limiting my session. So giving the coordinates, we are ISRI India, headquartered in Noida, providing GA solutions to more than 5,000 customers in different industries, which are being listed here. So ISRI builds RGS, which is a leading mapping and spatial analysis software for both desktop enterprise with geospatial capabilities like mapping, field operations with imagery analysis and spatial analysis. So in start with GIS, so this enables the geographic approach, which is a powerful platform for creating, understanding, exploring alternatives, or designing the solutions, explaining to others to take actions. So this is the life cycle where the GIS falls from the data collections to take the action. So as we see, the GIS is advancing rapidly with integrating many innovations from 2D mapping, 3D mapping to geo-designing. Now GIS is available both in web as well as the mobile with integrating imagery, remote sensing, and now it is available as a distributed system. So what we do for this GIS? So RGS is a comprehensive geospatial system which is supporting multiple communities who leverage these technologies using our foundational products like RGS Pro, Enterprise, and RGS Online, which is available as a software, as a SaaS, as well as a platform as a service. So this RGS supports many implementation patterns. It is a common platform which supports the shareable resources, which can be scalable, reliable, and in a secured environment, which is available as products is an enterprise as desktop. And we integrate the different data types which are present from the tabular data, vector, or multi-dimensional data, or the big data, or the point cloud data, all other data which are being listed. So it integrates into a single platform. Now the RGS is available as an open platform where the users around the world are putting their data in an open data platform which can be used for others, can be used in their different projects. So where we see the maps, datasets, and apps in a single platform. So it is an enterprise system where it is well architected platform which is supporting mission critical applications where it is bringing the GIS and IT professionals or other field operators into a single platform. So as we have seen, the GIS is advancing, even RGS is also advancing in putting their efforts in cloud computing, AI, ML, data science, or the big data analysis. So this is the other good option of which is we call as a living atlas of the world, where we do have 10,000 plus items in the software which can be readily useful, like as a maps or which is being updated continually. And we have the land use map, satellite images, or the climate layers which can be used in your projects. So as we also, the RGS is an open and operatable, so you can use it inside the RGS system, or we give as an open architecture or open APIs which can be used in other platforms also. So as we need to live with open, so we also, RGS is an open to integrate in your application. So this is an bread and butter of the platform, which is an RGS Pro, which most of the GIS user, geospatial industry use the product, which we have seen the lot of improvements we are doing, and in coming we are also giving the 3D tile supports or the flood simulation modeling into the platform. 2 minutes, yeah. So this is a web enterprise platform where we are also improving, which is a data management, mapping and visualization platform where you can use. And we are also supporting the Kubernetes. So already we do have on Windows and Linux. So in order to scale up your operations, so now we are also supporting on Kubernetes platform, where we are also coming in future release, we also support the video server or the Kubernetes enhancement. So this is some of the mapping capabilities. So as you see the climatic or ocean data, this is a new map viewer in enterprise where you can see the dynamic visualization and animation. So people are interested in interactive web mapping, so we are going to support that. And this is some instant apps where you can create some instantly if you want to create your web maps to convert to web maps. So we have a readily 18 plus templates which are you can easily configurable. And this is an dashboards where you can give as an visual reporting, which is an easy configurable. We call it as a no code or low code, where if you want to decision. And this is the new JavaScript 4.x experience framework for designing your web apps. So as we say that it is a low code environment where you need not be a programmer, just you configure and use it. So in the interest of time, I'll be skipping something. So this is for the Excalibur. It's a lightweight web app for your image exploration tools where you can do different types of analysis. And we also provide the APIs and SDKs to extend your applications and you create new apps. Yeah, once. Finally, because of, and even in interest, just I'll say we have a geo models. Everyone is talking on artificial intelligence. We have predefined models which you can readily work or you can refine them. So let me finish off. Some of the, I'll finish this one. So these are some of the global example use cases which people around the world presented in different, so they are using for their biodiversity sequence, climate analysis. So these are some of the which are being available on our website. You can just type RGS plus ocean. So there are a lot of hubs, the resources, the analysis which you can see. So even we are good at imagery also. So these are the things. So these will be our next roadmap. So because of time limit, so I could not keep it. Thank you very much. Thank you everyone.
I invite Mr. Balakrishnan, Director, Tridal Technology, to give his talk.
Good evening, everyone. I'll keep it very much short as possible. As name deciphers, we are into environmental solutions. We are a turnkey solution provider for environmental studies, data collection and management. Our USP is connecting environmental science, engineering and technology. Our portfolio is geoscience, study of environmental, geoinformatics, collecting of environmental data, geoengineering, managing of environmental data. We are operating in 4 locations: UAE, India, Australia, Saudi Arabia, 50 plus people, predominantly Indian. We have served almost 15 plus countries and 150 plus projects. Some of our credentials: the turnkey solution providers in terms of ecology and biodiversity studies, customized software development, environmental monitoring, surveying and mapping, marine construction and support services, design and construction of survey platforms, design and manufacturing of customized buoy platforms, products, software products, integrated data collection softwares, tidal analysis and modeling software, eSpecia, our smart biogeoinformatics software, TSMS survey workflow management software, geodatabase, spatial database software, SIMS smart inspection management software. I'm not going into detail. The brochures and technical details can be discussed in the stands. Our products, in terms of hardware products, we manufacture buoys and deliver across the globe. TNB, tidal navigation buoys, TDB, tidal data buoys, TCB, tidal coastal buoys. These are our prominent clients in terms of data buoys. Our winches and lot system, we manufacture our own winches, right from smaller profiling winches for buoy installations to a bigger capacity of 1,500 meter capacity winches and launch and recovery systems. Then customized survey platforms and customized integrated systems like vessel-based eddy covariance systems, vehicle-based air quality systems, or groundwater monitoring, autonomous camera-based beach monitoring systems. References and solutions, I'm keeping towards the theme of the event, that is operational oceanography, science and services, related to sub-themes like ocean observations. As I told, like we do a lot of ocean observation platforms of various customized platforms for NCCR, Dubai Municipality. This is a very customized platform for National University of Singapore with the profiling winch mechanism for water quality monitoring, and deep water buoys installed in Lakshadweep by NIOT, again for installation in Dubai canals for water quality monitoring, shoreline monitoring, customized data buoys for NEOM in Saudi Arabia, again with the profiling winch and central moon pool mechanism, mid-ocean buoys and tide med stations for Qatar, major international ports and National Center of Meteorology. So almost 30 plus buoys has been operational, deployed and been operational, and customized coastal process and related to sub-theme of RC interactions, vessel-based eddy covariance flux system installed on Sagar Nidhi, which is now upgraded with sea surface temperature, weather stations, and camera-based coastal monitoring system for shoreline erosion monitoring. Then coastal process in terms of data collection. We do conventional vessel-based bathymetric survey, and we have solutions for the aerial topo bathy lidars, and biodiversity, ecology, marine resources. One of the key talk which I do now, environmental studies is for the sake of, not for the purpose. So where we do some environmental studies like coral reef studies and translocations, artificial reef placements, integrated fisheries management plans, I think types, yeah. So trackings of this thing, and last few latest technologies in terms of ocean engineering, the infinite float, which is powered by ocean temperature differences, and smart buoys. These are clienteles. Hope I kept it on time. Thank you.
Thanks a lot, sir. Our last speaker for the evening is Mr. Mukalingam, Lead AI Engineer, Spotflock Technologies.
Yeah, good evening, one and all. So, this is not okay. So about us, like we are an AI-based company founded in the year 2017 in Hyderabad. So we are a deep tech based company. So we do have our own AI-based platform, so which is an API-based as well as platform as a service. So it can even it can serve around 26 ready-made tailored solutions for around 5 verticals, and now I can say like we have even entered into the other verticals, so-called oceanography, and we do have 3 patents till now, like one is into intelligent machine learning, other one is flock engine, and the last one is IoT CV. So with Incois, we have been tied up for giving AI-based solutions. Like since the past few months, we have been working with the Incois team for giving one of the solutions. I can say that predicting the HF radar ocean currents using deep learning. So we have been working with the team of Incois since past few months. So we are in process of giving the solution for it using our AI-based platform. So I'll just brief down the new use case which I've just got recently. So I'll skip my introduction and all of the stuff. So the thing which I wanted to talk today is marine species detection and tracking using deep tech. So there are vast kind of marine species in the all over ocean. So we can even use AI things to detect which kind of species it is and what all can be done, like what all analytics can be driven by detecting these all things. So I'll directly go into so this is how we plan to give the solution for it. So initially we'll be taking the video data, then we'll process it using some data pre-processing techniques. Then this is the main part, which is object detection and tracking. So here we'll be detecting the species, area occupied by that particular species and types of species. And I just mentioned about the deep tech models which we'll be using for giving the solution for this. And there are lots of other deep tech models where we can use for detecting the species. And the final output will be like kind of reports, or you can even, I'll just show a small dashboard. So this is what the dashboard which we are planned. So here we can analyze lot more things, like I restricted only 8 parameters here. We can even include much more parameters, like I just mentioned the numbers as random because we haven't analyzed the whole data yet. Once we get some kind of data, then we can analyze these all parameters for that particular species detection. So one is number of species detected, the other one is number of species tracked. Tracking in the sense like once the species is detected, it will move from one place to other place, right? So that can be tracked using our AI solution. And other one is longest migration route, average species boundance, species hotspots, like these are very important for fishermen, recommended fishing practices, restricted fishing zones, and the rare species. I can say like for the rare species which are like very dangerous for the marine ecosystem, that can be done by using AI. So what are the advantages of using these kind of solutions? So one is biodiversity. I'll just close it last. One is biodiversity monitoring, other one is conservation planning, other one is sustainable fishing, which I have already shown about few things in the last slide. And last one is environmental monitoring. Yeah, I think I'm done. Thank you all.
Thank you. We are bringing the curtains on this intellectually stimulating program. I'll be delivering the vote of thanks. It's my privilege to extend a heartfelt vote of thanks on behalf of the entire organizing committee. We are profoundly grateful to each one of you for gracing this occasion. A heartfelt thanks to Dr. S.S.G. Shenoy for his profound insights through the plenary talk. I extend my sincere appreciation and thanks to Dr. Mani Murali, who guided us through the evening's proceedings. My sincere gratitude to all the industry representatives for their talks. we'll have more engaging conversation. I encourage all the participants to meet them at their respective stalls in the first floor. I would like to express my gratitude to Dr. M. Bala and Professor Prasad Prabhakaran for the OSI award. And thank you, Patabi sir, for unveiling the OSI Fellow 22. And special thanks to Dr. Srinivas Kumar for your guidance, sir. Once again, thank you all for your participation. We will have an enriching evening during the dinner, which is sponsored by Pan India Consultants. I would like to extend my heartfelt gratitude to them. Thank you. Thank you all for joining us tonight. See you tomorrow, the last day of OSICON 23, which will be filled with more interesting talks, sessions, and discussions. Good night.